All right, welcome to our presentation on the group 14 elements. My name is George.
I'm Donnie.
And I'm Dennis. So just some properties of the main group elements. As you move from the left to right across the periodic table, elements tend to have a greater electronegativity, a smaller size, and an increased ionization energy due to an increased effective nuclear charge from nuclei with more protons. And then as you move down the rows of the periodic table, elements tend to have lower electronegativity, larger size, and lower ionization energy. This is due to the shielding effect, which occurs from the inner electron shells shielding the valence electrons from the nucleus, leading to less attraction. While some exceptions exist to these trends, like small increases in size due to new subshell filling or small decreases in ionization energy due to electron-electron repulsion, these trends show a general pattern across most of the elements in the periodic table. So some commonalities and differences between the group 14 elements. Some commonalities is that they contain metals, nonmetals, and metalloids in the same group. They're extremely versatile and unique bonding structure for each element. Some differences are like carbon is extremely safe, but then there's also extremely toxic elements like lead. There is an increase in ionization energy from tin to lead, and then the relative abundances of each element in the group 14 main group does differ. And so the group 14 elements compared to other main group elements, some commonalities are that carbon can also accept ligands and form complexes like palladium, platinum, and iron. And then carbon can also form bonds with other organic atoms to create bioactive molecules like the one shown on the right, paclitaxel, which is a chemotherapy drug. And so carbon can form bonds with oxygen and nitrogen to create this bioactive molecule. Some differences are the valence electron count between every main group. And this difference in valence electrons will lead to a difference in effective nuclear charge. So halogens have a higher effective nuclear charge. They will be a little bit more stable in comparison to the alkali metals, which will be a little bit more reactive due to their less effective nuclear charge. And then group 14 will have a nice medium relative to halogens and alkali metals. And so looking at the element with the lowest atomic number in group 14 is carbon. Carbon is the basis of life. It's known for its abundance and versatility in biological applications. It easily undergoes hybridization and has a very stable bonded structure with 4 bonds. Another unique application of carbon is its use in polymer science. Carbon's a very efficient element for polymerization reactions, and this is just a process in which small monomer fragments become attached to a long strand, forming extremely stable, strong, and versatile materials like polyethylene chain shown below. Carbon can also form high coordination number complexes, and then the coordination number of an atom is simply just the number of atoms bonded to the central atom, carbon in this case. Carbon can also form nanomaterials, including fullerenes, as shown below. And then surrounding the fullerene is a graphene nanotube. And then graphene consists of multiple layers of carbon atoms, and then it can be cut into strips that are called nanoribbons using lithographic techniques. And then the edges of these nanoribbons can be joined together to form nanotubes. In the top right, you can see our carbides, and carbon can form carbides when combined with a metallic element. And these are becoming increasingly used due to their low cost and high durability, as well as their recyclability in consumer products.
All right, so next up, we're going to talk about silicon. So silicon has many similar properties to carbon in its electron affinity, ionization energy, and it also has likely bonding partners of that include hydrogen and oxygen. However, though, it is generally less stable. Silicon can form bonds with hydrogen to make silanes. The most stable silanes has the chemical formula SiH4. Most other silanes, especially with other silicon bonds, have a very high decomposition rate. Another use of silica is that it can form bonds with hydrogen to form or oxygen to form silicate materials. Generally, silicate materials are inorganic compounds consisting of subunits with an increasing number of silica atoms with 2 oxygen molecules for each silica. This has only been able to be done up to 8 silica atoms, though. An example of a silicate material is glass. Other bonding of silicate includes a diamond structure, a square structure, or even pyramidal units. Silicon can also readily react with halogens to form silicon halides. Semiconductors are made from pure silicon materials. Also, the process of doping can manipulate the silicon band gap in these materials, and that's shown in the next slide, in the bottom left corner here. Also, silicon carbide is one of the most versatile silicon products and can be formed in a diamond or quartzite crystal structure. It can be used as an abrasive or a high temperature semiconductor. Next up is germanium. So it is a hard, brittle metalloid that is stable in air and water in its elemental form. It is considered a semiconductor by definition. So germanium can also exist as a halide, in which GeX4 is the most stable form. And on the slide is an example of that, where the X4 is used as chlorine instead. So GeCl4. It can crystallize in the diamond structure, but it forms weak covalent bonds due to the inefficient orbital overlap, which prohibits greater chemical reactivity. So similar to the plight of silicon, its growing chemical radius also prevents it from reacting with most other atoms. Like silicon, it can be used in manufacturing semiconductors. It is mainly used for fiber optic systems and infrared optics. Next up is tin. So tin has many uses. One of them including it could be used as a polish that can coat other metals to prevent corrosion. It has an extremely limited reactivity. It has low-lying d orbitals which can accept electron pairs from nucleophiles. There are two allotropes of tin, which include a diamond alpha form and a metallic beta form. Stannane, which has a molecular formula of SnH4, is tin with an oxidation state of +4 and is relatively unstable. It can form some compounds in its +4 oxidation state with more stability. Tin can also form chalcogenide derivatives, which include tin oxides, tin sulfides, and tin selenides. Tin 2 chloride is the most important commercial tin halide. It is used widely as a reducing agent in acid solution.
And then the last element that we'll consider in the group 14 elements is lead. Lead has an extremely limited reactivity in comparison with some of the other group 14 elements, as it mostly forms ionic bonds, unlike some of the more commonly covalently bonded group 14 elements. Its 2+ oxidation state serves as its most stable form, similar to the other elements in group 14, as it can react with many halide species this way. Lead's ability to form a cubic lattice with sulfur allows it to be used in semiconductor applications as well as for sensors. Lead 4+ is pretty rarely seen, but it has been documented. The graphic below shows lead 4 in its complex with acetate. This was used for organic chemistry applications like Lindlar's catalyst, but it is increasingly becoming phased out. The oxidation state of lead and lead ion in 2+ or 4+ is similar to many natural ions found in the body, and therefore it is being less used because it can be quite toxic. And then next, we're going to discuss some interesting facts about some of these group 14 elements. Carbon is discussed extensively within the textbook, so we decided to focus on some of the lesser known elements with these facts. The element germanium is known for its exceedingly high refractive index in its crystalline form. The extremely low gray line in the percent transmittance graph here shows that it has relatively high refractive index and low percent transmittance for wavelengths above that of visible. And so therefore it's used often for optical instruments, including beam splitters, which are found in spectrometers or interferometers. The utility of germanium crystal is arguably higher than that of any of its other forms due to its general lack of reactivity, as shown in previous slides. Another interesting phenomena of group 14 elements is the increased use of tin within lithium-ion batteries. Tin being known for its lack of reactivity, especially in the 4+ oxidation state, is often used to protect anodes. In the continuous process of recharging and discharging, a common problem in batteries is the corrosion of anode materials in the electrolyte solution. The tin atoms seen in red in this picture, coupled with the sulfur atoms seen in yellow, show a groundbreaking stable anode that has recently been invented. It is highly resistant to corrosion and does not fall victim to the volume expansion problem that many tin electrodes have recently experienced. The tightly bound crystal structure of the tin chalcogenide lattice prevented lithium atoms from entering. demonstrating it is resistant to corrosion and volume expansion as an anode. Finally, a recent computational analysis has discovered a new allotrope, which can be found among almost all of the elements of group 14. Using Calypso code and density functional theorem optimization parameters, mass generation of different structures yielded this tetragonal structure. This was generated using a particle swarm structural search, where this team in this paper fed data of thermodynamically stable sp3 hybridized allotropes of the elements carbon, silicon, and germanium into a computer. This paper describes a likely synthesis of a crystal by taking high pressure silicon or germanium-2 and decompressing it under a variety of heating conditions. And this really shows that the group 14 elements, despite having different reactivity and varying stabilities, whether it's in solution or in crystalline form, can sometimes all have identical outcomes, which is really unique in comparison to the reactivity of some of the other groups of elements across the periodic table. This differentiates the group 14 elements from the others and shows that their bonding properties are unique altogether.